Okay, so our speaker today is Francesco D'Andrea, and his title, as you can see there, is On the K-Theory of the AAF Core over Graph System Algebra. Please, Francesco, go ahead.
Yes, so thanks for the introduction and for the invitation. So I'm very happy to give this seminar to the, let's say, competing seminar of South Atlantic non-commutative geometry. So I think I already gave a seminar for this series when it had a different name. It was the Global before, Global, I don't know if it was the same.
No, the global version. So I was
Included Argentina, right?
I was an organizer among other people, but other organizers involved so were Alain Cohn and Nelson Hickson, and I think it was William Yu and Masoud Al-Khali.
Yeah. Okay, so anyway, it is really a pleasure. And so the topic today, I want to talk about, in some sense, about multiplicative structures on the K-theory of some class of sister algebras. And actually, I already gave this talk in some sense, in the South Atlantic, in Brazil, in Florianopolis. So I hope not too many people are listening about this again. But I think it is it is an interesting topic. I'll try to motivate it and convince you that it is there is something interesting behind this. So this is about multiplicative structures in K-theory. So, and what is the motivation? Let me start with the commutative sister algebra, which means functions, continuous functions on a topological space. My space X will always be compact and Hausdorff, and my sister algebras are always, well, first of all, over the complex numbers and unital. So if A is a C of X, then you can take two A modules, one-sided modules, and it makes sense to take the tensor product over A because every module is in particular, you can think of it as a symmetric bimodule. And the direct sum and tensor product over A give you induce a ring structure on the K-theory of the sister algebra, which is also the K-theory of the space X. There are different interpretations of this module structure, so you can think of it if you, from a topological point of view, if you think of elements as differences of classes of vector bundles, then the operations are induced by the Whitney sum of vector bundles and tensor product. Okay, so if A is a commutative sister algebra, K-theory of A, the K-theory of A, and for me K-theory today is just K0, it is not only a group, but is actually a ring. On the other hand, if A is a non-commutative sister algebra, K0 of A is an abelian group, there is no canonical ring structure. So what we would like to do is to put a multiplication on K0 of A that in the commutative case reduces to the standard one. And why we want to do this, I have a naive example. I had also a less naive example, but I thought, okay, that would take too much time. So I think this is enough to convince you. This naive example is, well, we have two spaces. So one is the disjoint union of two closed disks. And the other one is the unit sphere in two-dimensional one. So if you compute K0, in both cases you get something in which an abelian group as an abelian group is zeta to the power 2, and but the ring structure is different. So on the left-hand side, K0 is generated by two orthogonal idempotents. So you get a zeta to the power 2 as a ring with component-wise multiplication. And for the sphere, what you have is a ring of truncated polynomial, is zeta of x with the relation that x squared is equal to 0. So when you glue this to get a sphere, the abelian group structure of K0 doesn't change, but the ring structure does. Okay, I'm not talking about K1 because in all my example, K1 in fact will be 0, not because it is not interesting, but because first of all, we still don't know how to deal with it. And the second, in all this example is 0, so it really doesn't matter. Okay, so the ring structure is important even if you want to distinguish simple spaces like two disks and a sphere. You need to look at the multiplication. What to do in the non-commutative case? Well, there is a first answer that comes to mind is that you can look at kk of AA, which is a ring, but is not what you want already in the commutative case. Kk of AA is not the ring K0 of A, so it's a different ring and usually less interesting. And it is less interesting because for a large class of sister algebra, Kk depends only on the abelian K groups. So it depends only on K theory, and on K theory as an abelian group, so doesn't know about the ring structure, even in the commutative case. And the other problem is that what you get is not a factor, because Kk is covariant factor in one entry, contravariant in the other one. If you put the same algebra in both entries, you get nothing. So this is, unfortunately, this is not a solution to our problem. There is a work in progress, and here you can see the preprint number of a first version of this paper with Tomek from University of Warsaw, where we have an idea on how to get a multiplicative factor. There is a first draft online. It must be improved, meaning that we still have to work out examples and so on, but at least K0 works, so that it is well defined and has all the properties that you would like it to have. But I'm not going to talk about this today, so this is for maybe another talk. And what I'm going to talk about today is something different. It's a class of examples where K-theory has an additional structure. For this class of example, the motivation is, the motivation is complex projective spaces. So let me start recalling something about the K-theory, the classical K-theory of CPN. In fact, CPN minus 1 with n, where n is at least 2. So what is this K0? This K0 as a ring is, again, like for the two-sphere, which is CP1, is a ring of truncated polynomials, is zeta of x over x to the power over the ideal generated by x to the power n. And x is explicitly given, is 1 minus the class of L1, where L1 is what we call the offline bundle. So the offline bundle, it means if you want is if you take the off fiberation, which is a principal U1 bundle, you take the fundamental representation of U1 and the associated vector bundle is this L1. Okay, instead of L1, you could use the tautological bundle. It works, it is the same. You get the same presentation. Okay. So from this is a classical result of Ati and Todd, and from this you can derive several identities and several corollaries. First of all, if you call for k an integer, if you call Lk the power L1 to the power k, so this is another line bundle. For every k, Lk is a line bundle of Cpn minus 1. And it follows from this ring structure that powers of L1, the first n powers, they are a basis of K0 as a zeta module. So Lk, the class of Lk for k from 0 to n minus 1, this is the basis of this zeta module. And the identity that x to the power n, this is x, that x to the power n is equal to 0, can be rewritten using the binomial formula for this power of a sum of two pieces of two integer numbers. Using the binomial identity and using the definition of Lk, you can rewrite this as a sum for k from 0 to n of some coefficients, binomial and signs, times Lk equal to 0. Here we sum from 0 to n. From 0 to n minus 1, you have a basis of K0 as a zeta module, so they are in particular linearly independent, but here you have one extra, you have also Ln. Okay, so why did I write these two identities? These follow from the ring structure of K-theory of Cpn minus 1. And what was a bit surprising is that both 1 and 2 they are still valid for quantum projective spaces if you define line bundle in the correct way. So by quantum projective space, we recall the definition. I mean the ones sometimes are called Waxman-Soebelman quantum projective spaces. And well, actually, I didn't have to specify this because, okay. So for Waxman-Soebelman quantum projective spaces, these two identities, these are in a paper by Arici, Brain, and Landi, which now I didn't put the archive number, but I think maybe it was, if Gianni is online, he can tell us if it was 2015 or something like that. I'm not sure. A few years ago. These identities were proved again using groupoid sister algebras by me, Piotr, which should be, I see him online, and other people that I'm not listing because there was no space, sorry. But here is the archive number. So the other people are Tomek, Maszkik, Albert Shaw, Bartek Zielinski, and that's it. Okay, so you can find in this archive preprint this new proof using groupoid sister algebras, and the point is that this proof using groupoids also applies to another family of quantum projective spaces that are called multi-pullback quantum projective spaces, and I'm not going to talk about this today. Okay, so the point is you have these identities that survive quantization even if you don't have a ring structure for the case theory of a non-commutative sister algebra. Well, is it really true that there is no ring structure at all? What is the geometric origin of these identities? And how general actually these identities are? Do we have similar identities in case theory? Yes.
One question. So if there is no multiplicative structure, what is the meaning of L1 to the K?
Well, L1 to the K is only in the classical case. So this is how you define Lk classically. Then for quantum projective spaces, we will see what is the analog of these line bundles. For each K, you have a representation of U1, and you have something replacing line bundles that are invertible bimodules. But yes, this is the definition only in the classical case. Then there are analogous identities, but I will explain what they are in the non-commutative case. And I will try to explain that actually there is also a multiplicative structure. It is not so obvious what it is, but there is one. And I'm coming to the non-commutative case in a moment. But yes, this is classical, and the analogous identities that we have, 1 and 2, the analog of 1 and 2 in the quantum case, I have to explain still what it is.
Yeah, because I mean, one, if I mean, there is no specific choice of Lk, one only says that K0 is free of rank n, and yes. Two, if you, I mean, you can define Ln.
Yes, of course.
Passing it to the other side. And then...
yeah. No, there is a definition of Lk, but is not as a tensor power. I mean, then you will see that you can construct them as suitable powers because these will be bimodules instead of just modules in the non-commutative case. So you can actually take tensor product over the algebra, which is the dual version of tensor power of line bundles. And in fact, are line bundles in the sense that they are invertible bimodules. I will tell about this in a moment, but let me first say, so I want to focus on Waxman-Soebelman quantum projective spaces. And the point, even one more way to prove these identities that I will show is using graph sister algebras. And in fact, the idea, what I want to explain is that there is something that you can say in general about graphs, about the theory of graph sister algebras. There is some kind of ring structure, and from which similar identities can be derived. So let me recall, I will be fast on this because I think that, I mean, this is pretty standard stuff and many people here know what I'm talking about. So by a graph, I mean a set A0 of vertices, a set E1 of edges, and two maps that are called source and range maps from E1 to E0. By async, I mean a vertex that emits no edges, which means that there are no edges. The set of edges with source V is empty. In this picture, this is the picture of a special directed graph. Just to show an example, you can see that you can have parallel arrows and even parallel loops. Loops are allowed. There are basically no constraints on this graph. It can be anything. And V in particular, this denoted by V, is an example of sync. It emits no edges. So why do I need the sinks? Here I'm going to give the general definition of graph C-star algebra, but then we will focus on the case where the graph is finite and there are no sinks. And this is a definition slash theorem. I'm not going to explain all the history behind graph C-star algebras, but okay. So for every graph E, there is a C-star algebra, C-star of E, which is generated by mutually orthogonal projections, one for each vertex, and they are denoted by PV, where V is a vertex, and by partial isometries with orthogonal ranges, and these isometries for E and edge in E1, the corresponding isometry is denoted by SE, which should satisfy some relations called usually Kunz-Krieger relations. These are the three relations that you see here. This C-star of E is universal in a suitable sense. You prove that it exists. And I'm being a bit sloppy. I'm not going to say what I mean exactly by universal because it would take time. But what you show is that such a C-star algebra exists. So what are the relations? I mean, universality you need if you really want to work with the C-star algebra to show that it has some algebraic properties. So the relations are that for every edge E, SE star SE should be the projection of the range of E. So for example, if E is this edge in the picture, in the green picture, and you take the corresponding partial isometry, SE star is the projection of this vertex that I don't know if can you see the laser pointer, the red one? Yes, okay. So SE star SE is the projection of this vertex. There is a relation number 2 that I'm going to skip because it's redundant. You don't need it when E is finite and with no sinks, so I'm just not going to read it. Relation number 3 tells you that if you look at all the edges starting from some vertex V, and you sum SE star over all edges E with a fixed source, then you get the projection of the source vertex. And this makes sense. You have this relation whenever the set of edges starting at V is non-empty and is finite. Okay, so it follows from these relations that this graph C-star algebra is unital if and only if you have finitely many vertices, and the unit is the sum of all vertex projections, and we are going to denote this by 1. And this is the framework I'm going to work. Given any graph E, you can define, it is well defined, an action of U1 on C star of E, which here is denoted by gamma and is called the gauge action. By definition, this action is given on generators by the following formulas. So projections are invariant. If T is any element of U1, the action of T on a projection doesn't do anything. The action on a partial isometry, SE, rescale the isometry by T. So this is the action on the other generators, the partial isometries. Okay, in particular, using this gauge action, you can split your C-star algebra in several pieces, in several vector subspaces. For every k integer, you can call Lk the set of elements in the C-star algebra, such that the action of a unitary T on A is given by T to the power K times A. So these are the elements that we call of degree K. And if you take the direct sum, each LK is a vector of subspace of C star of E. If you take the direct sum, this direct sum is dense in the C star algebra. So you recover almost all the C star algebra. L0 is a C star subalgebra, and is what we call the core of C star of E. L0 is the set of invariant elements under the action of U1. And we think usually of LK, of elements of LK as kind of sections of a line bundle on the quantum space described by L0, because this is the classical picture. So you can think of C star of E as describing functions on the total space of some principal bundle, where U1 is the structure group. L0 will be function, well, classically would be continuous functions on the base space of this bundle. And for each k, Lk is the set of the space of sections of a line bundle constructed, which is associated to this principal bundle and constructed using a representation of U1. So this is the classical, let's say, the classical interpretation of this kind of things. For us, is just, I mean, is a geometric way of thinking of these objects. So each LK we think as a set of sections of line bundle on the quantum space dual to L0 in some sense. Okay. So it's not just, what we get is not just the decomposition in vector subspaces. If the graph, well, in general, this is a graded algebra. So if you multiply an element of degree k and an element of degree j, you get an element of degree j plus k. This is always true. I mean, this just comes from the definition. And but if the graph is finite with no things, you have more. You have that Lj times Lk is equal to Lj plus k, meaning that every element of degree j plus k can be written as a sum of elements of product of elements of degree j and k. So usually you just have inclusion. In this case, you have equality. And when this happens, we say that we have strong grading.
So is there an if and only if condition? So
if you want a unital C star algebra, it is if and only if. So the C star algebra is unital and strongly graded if and only if is finite and with no sinks. In the non-unital case, there is an if and only if, but it's more complicated, so I'm not writing down the relations. But you find it in this paper by the guy that I listed here, Harsrat, Clark, and so on. So they have if and only if also in the non-unital case, but is more complicated to explain. Here is very simple, finite with no sinks, and that's it. Okay, so why this is interesting? Whenever you have a strong grading, what happens is, in general, Lk is always a bimodule over L0, and the bimodule structure is just given by the multiplication inside the big algebra C star of E. This is always true. But if you have a strong grading, Lk is an invertible bimodule, or a self-Morita equivalence bimodule, if you want to call it, like that. And you have for each j and k, the tensor product over L0 of Lj and Lk is isomorphic as a bimodule to Lj plus k. So you have this isomorphism of bimodules. So in particular, this means that these bimodules in particular are one-sided finitely generated projective modules. So they define an element in K0 of the C star algebra, in K0 of L0 of the smaller C star algebra. And this tensor product of these elements induces a kind of multiplication in K-theory, which is just given by is a very simple one, correspond to the multiplication inside the big algebra. So this isomorphism of modules is just to say that you take the tensor product over L0, or you multiply these bimodules inside the big algebra, and you get the same. This is just to give an idea of why I'm mentioning this, but I will be more precise soon. Okay, so this is the first tool that we need, the gauge action, and under these assumptions, if finite with no sinks, we have something that replaces line bundles, for example, over complex projective spaces. Instead of line bundles, we will look at this kind of objects. And this is canonical. Whenever you have a graph, you have this gauge action and this decomposition. But it depends, different graph can give isomorphic sister algebras, but different decompositions, different gradings. So if you this depends not only on the sister algebra, but on the graph that you choose to use to represent it. Okay, so there is some notation that maybe I can be a bit fast on this. Okay, this is just standard notation. By En, I will denote if E is a directed graph. By N, I denote the set of paths of length N, which means sequences E1, E2, En of edges such that the range of each edge is the source of the next one. And vertices are considered as a path of length 0. So a path of length 0 is simply a vertex, which is consistent because that is the notation E0 for the set of vertices. And a path of length 1 is an edge, is E1. Given if alpha is any path, any finite path, you can define a partial isometry as alpha, which in the case of length 0, if alpha is a vertex, is just a projection PV. PV is still a special partial isometry. And if alpha is E1, E2, En, then S alpha is defined as the product SE1, SE2, SEn. So in this way, you have a partial isometry S alpha for every finite path alpha. And this will be an element of degree n, where n is the length of the path, meaning that because of the way the gauge action works, each projection is in L0, it's something of degree 0. Each SE1, SE2, SEn is degree 1, and then you multiply the degree. If you have a product of n such partial isometries, you get something of degree n. Okay, so this has degree n, the adjoint of S alpha will be something of degree minus n, and you can prove that Lk, in fact, is the closure of the span of monomials of the form S alpha S beta star, where alpha and beta are paths such that the length of alpha minus the length of beta is k. So this the only constraint is that this has the degree k as the correct degree. You take all of them, and they span a dense subset, a dense subspace of Lk. You know also how to multiply these elements, so everything is really explicit. If you have two such partial isometries, their product is basically concatenation of paths, and if they cannot be concatenated, the product is 0. And there is also a rule to multiply the adjoint of a partial isometry to a partial isometry as alpha. So as beta star as alpha is if beta is an initial subpath of alpha, which means that alpha is beta concatenated with some path mu, then this guy is as mu, you just simplify beta. If alpha is a subpath of beta, so beta is alpha times some path mu, you simplify alpha, and what you get is that this guy is S mu star, and in every other case you get 0. So basically, this is just to explain that everything is really explicit. You can compute basically everything, and using these relations, you can prove the following. This is what I'm going to explain now is basically is explicit in the book of Reborn on graph sister algebras, except for different conventions about directed graphs. So what I want to explain is that this L0, the core of a graph sister algebra, if the graph is finite and there's no sinks, this is an AF algebra. It has a dense subalgebra. Let me say the simplest way to say this is that the core, while it's written here is in blue, the core is as a dense subalgebra, which is a union of a nested sequence of finite dimensional subalgebras. Or if you want to say it in a more complicated way, is the inductive limit of finite dimensional sister algebras. Okay, so take E finite with no sinks, and for any integer, let me call ENV the set of all paths of length n whose range is the vertex v. So n is the length and v is the range of the path in this set. Since I am assuming that E has no sinks, En is always non-empty for every n. You have a path of arbitrary length, but E and V could be empty for some vertices V, so this could be still empty. If it is not empty, if E and V is not empty, I call A and V the span of S alpha S beta star, where alpha and beta are in this set, in E and V. And this is actually for the product rules that I told you before, this is actually a subalgebra of our graph sister algebra, this is A and V. And then I call AN the sum, the direct sum over all V in A0 of A and V. And this is also another subalgebra of our graph sister algebra. So one can show that in general, these elements S alpha, S beta star, if you take all of them, they span the graph sister algebra, but they are not linearly independent. If you consider only the elements with alpha and beta in the set double dagger, which I don't see now, in the first set, in E and V, then because of the constraint on the length and on the range, these elements are linearly independent. And this means that A and V is finite, of course, it's finite dimensional because you have finitely many paths of length, of fixed length n. And but you can also compute the dimension. The dimension is just the number of such paths. Well, not the dimension. This is a matrix algebra where the order of a full matrix algebra with entries complex numbers is isomorphic, where the size of this matrix is the cardinality of the set E and V. Okay, so we will see in a moment it is not difficult to show that AN, which is the direct sum of this A and V over all vertices V, AN is a subalgebra of AN plus 1, in fact, a unital subalgebra for every integer n. And if you take the union, so it makes sense to take the union over all n of this AN, since each one is contained in the next, and this union is a dense in the sister algebra that was denoted L0 before, this AF core. Okay, fine. So this is exactly what we call an AF algebra. Now, the structure of this AF algebra can be read, I mean, they are described for people that are familiar with this, but something called Bernoulli diagrams that tell you how each algebra is embedded in the next. And these embeddings are also quite explicit. It can be read explicitly from the graph E. And this is what I want to do now. So let me call gamma with entries gamma VW. V and W are vertices in E. For every pair of vertices, I denote by gamma VW. Well, gamma VW is the number of arrows from V to W, which is finite because I'm assuming that the graph is finite and with no sinks. And this is what we call the adjacency matrix of the graph E. Since the graph has no sinks, for every path alpha and beta of with the same length n, as alpha as beta star, using a Kunz-Krieger relation, you can show that this is equal to S alpha projection range of alpha as beta star. If you insert inside the range of projection, you do nothing. This acts as the identity on the right of S alpha and on the left of S beta star. And here I'm assuming that alpha and beta have the same range, otherwise this product is 0. And you can use the third Kunz-Krieger relation to write this range projection as the sum over all edges which source this vertex of SE star. So this that you see in red is the relation number 3 in the definition of Grassi-Star algebra. So from this identity, you can see how these finite dimensional subalgebras are embedded one into the next, because here I take a basis element with path alpha and beta of some length n and the range some vertex v, and I rewrite this as a sum where now I have path of length n plus 1, I have alpha concatenated with e with some edge, and this is something in an plus 1. And you have, in this embedding, you can see that ANV is embedded in an plus 1W whenever there is at least one edge from V to W, and the multiplicity, in fact, of the embedding is given by the number of edges, so it's given by this gamma VW. Okay, from this you can, if you know what Bratelli diagrams are, you can write down explicitly the Bratelli diagram. The Bratelli diagram of C star E U1 has the gamma VW arrows from this algebra to this one for every n and for every V and W. In particular, it starts with one-dimensional algebras. For n equal to 0, the path of length 0 are vertices, and from the definition of A and V, you see that A0V is just elements proportional to the projection of V. And you can also compute using the adjacency matrix the size of matrices of the matrix algebra A and V, the cardinality of this set, the set of path of length n with the range V, while the cardinality is just given by this sum. Gamma n matrix element, gamma to the power n matrix element VW is the number of path of length n from W to V inside this graph. And if you sum over all W in E0, you get the cardinality of this set. Okay, so example, take this graph with two vertices, one arrow from one vertex to the next and one loop. It is not difficult to show, you can do explicitly, but okay, it is something well known. The C-star algebra V is 2 times 2 matrices with entries given by continuous function on S1. What is the Baratelli diagram of the AF core of this graph? So you start with 2 copies of C, one for each vertex. Then you have exactly 2 paths of length 1, 2 edges, which means that the next algebra is M to C, and each one is embedded with multiplicity 1 because you have one arrow from one vertex to this and one arrow from one vertex to this. So one arrow corresponds to this and the other is the loop. And this algebra, you can imagine that is attached to this vertex. This is the only vertex that is the range of paths of length 1. So then you go to path of length 2. There is a none with a range this vertex here, and there are exactly 2 with a range this vertex here, and you get again 2 times 2 matrices. And now this is embedded here with multiplicity 1, and this embedding is correspond to this loop here, and so on and so on. And you can see that it becomes constant. This diagram, the limit is just what you get is that the AF core is M to C. It's 2 times 2 matrices, but with constant entries given by complex numbers. Okay, so this is very general. From the graph of V, you can write down the Bratelli diagram, which I draw horizontally instead of vertically just because for a matter of space. But at each level, the diagram has, in principle, one node for each vertex of the graph, but some of the nodes would be associated to zero-dimensional algebras, so you don't see them. And from one level to the next, you connect the 2 nodes only if and only if they are connected in the graph key. The corresponding vertices are connected in the graph key. I will give a few more examples. Okay, so there is one more way to look at this core of graph sister algebras. Given, let me use this notation. Given a relation R on a set X, I will denote by X over R the groupoid whose R rows are given by elements in R, objects are given by elements in X, and the source and range map are the usual one, are the projections from R to X on the two factors. R is a subset of X cross X. Okay, so it is a theorem that every AF algebra is a groupoid sister algebra. This is general, not only for the core of a graph sister algebra. And if you know the Bratelli diagram of your AF algebra, you can also write down explicitly the groupoid. So the groupoid is given by, well, the set X is given by a right infinite path in the Bratelli diagram, and the relation is the relation of tail equivalence. You have to put a topology on this set and on both on X and on R. There is a canonical way to do it, but I'm not going to explain it because it would take too much time. What you get is an étale groupoid, and you can look at the sister algebra of this groupoid, and this is isomorphic to your AF algebra. Let me skip a couple of remarks. I just want to say that these groupoids are étale, as I said it, and amenable in particular. Amenable means I'm mentioning this because it means that I don't have to explain C star of the groupoid if it is the reduced of core full groupoid sister algebras. In this case, they are the same. You don't have to worry about these details. Okay, so examples. In this first example, the graph is the graph as one vertex and two loops. This is a well-known, the well-known graph of Kunz algebra O2. O2 is the big algebra C star of E. Inside of this algebra, we have these line bundles and this AF core. What is the AF core? Well, the Bratelli diagram now of the AF core has one node at each level. So for each n, you have a single algebra AN of V. So I draw one node at each level. And you have two arrows connecting each node to the next one, corresponding to these two loops. And what you get is the Bratelli diagram of the well-known car algebra. So in this, I draw the Bratelli diagram just because I want also to write down the groupoid. You can label the arrows, the top one by 0 and the bottom one by 1. And you can see that now with this labeling, a right infinite path, well, what I didn't say is that in the groupoid sister algebra realization of this AF core, in the theorem that I mentioned before, I'm looking at a right infinite path starting from the root. And a right infinite path here is just a sequence of zeros and ones. It's a binary sequence. So the AF core, you can see it also has the groupoid sister algebra of the groupoid given by binary sequences modulo tail equivalence. Okay, next example. I want to give still two more examples maybe, and then or maybe at least one. So in this example, he has two vertices, two loops, and one arrow from one vertex to the next. And this also is not completely obvious, but you can write down an explicit isomorphism between C star of E and the C star algebra of Voronovich quantum group SUQ. The AF core, the gauge action on C star of E correspond to the U1 action on SUQ2, the obvious one, which for Q equal to 1 is given by left multiplication. You embed the U1 diagonally on SU2, and the action is the pullback on the sister algebra is the pullback of the action on the group by left multiplication. Classically, the quotient SU2 over U1 is CP1, and in the non-commutative case, Q here is the deformation parameter. In the non-commutative case, is kind of deformation of CP1, which divided by CP1. Q is this Waxman-Soebelman quantum projective line, or also called the standard Podlish sphere. So what is the Brattelli diagram of this core of the graph-system algebra? Now you have two vertices, which means that each level in the Brattelli diagram you have two nodes. Your algebra AN for every n is direct sum of two full matrix algebras. You have to add the root. This is something I did not explain. These are the vertices corresponding to the one-dimensional subalgebras of elements proportional to the vertex projections, but I have to add the root for the groupoid picture. And from each level to the next, the embedding is given by top vertex going to the top vertex because of one loop, bottom vertex going to the bottom vertex because of the presence of the other loop, and then you have one arrow from one vertex to the other, which is here corresponding to this arrow going down. And you have no arrow going up because in E there is no arrow from the second vertex to the first. Okay, I don't know if it is completely clear. I mean, I'm trying to explain how to pass from the graph of the graph-system algebra to the Brattelli diagram basically by examples, because giving the general recipe is more complicated, it takes more time. But again, you can again play the same game of labeling arrows by 0 and 1s. 0 if the range is on top and 1 if the range is on bottom. And you can give an explicit description of the groupoid. Now objects, right infinite paths are either the zero path, the null sequence, or a sequence which at some point is definitely 1. So a sequence which is a tail equivalent to the constant sequence given by all ones. The relation is the one of tail equivalence, and there are only two classes. You can see this is a nice example because you can see that you have only two classes of sequences, the class of the zero sequence and the class of the constant sequence given by 1. And the fact that you have only two classes means that if you look really at the quotient space and not at the groupoid, the quotient space is formed by 2 points. And you can see this at quantum level because this is sister algebra, in fact, is Morita equivalent to a 2-point space. If you look instead at the groupoid, well, the groupoid sister algebra also has an explicit description, is isomorphic. This groupoid is isomorphic to some subgroupoid of the action groupoid zeta cross zeta bar, but I have no time to explain maybe what is this. So let me skip this and let me skip.
Sorry, I have a question. What is the rule by which a quantum group is, or the algebra of a quantum group is a graph algebra? Which graph algebras correspond to quantum groups? So how do you know?
Well, this is a very good question because the only example that we know are U1 and SUQ2. So, and
there is no general.
There is no general rule, and also for SUQ2, for SUQ3, for example, it is known that it is not a graph sister algebra, but it is an higher rank graph sister algebra. And also for SUQ2, okay, this is a graph sister algebra, but you don't see, there is no natural way to see the quantum group structure from the Kunz-Krieger generators. So the coproduct is something horrible in terms of Kunz-Krieger generators. Because basically the graph sister algebra is what you get when you put Q equal to 0. And then the SUQ2 sister algebra is independent of Q. But the coproduct depends on Q. And when you put Q equal to 0, you lose this nice formula for the coproduct, basically. Okay, so let me maybe skip examples and skip to the general result. Okay, so what I want to do, I don't have much time, but I'm trying to at least to show the general result. So the algebra that I want to study that now from now on equal A is the AF core of the graph sister algebra of E, where E is finite with no sinks. We have these LKs that are replaced line bundles on this sister algebra. And now with these LKs, we can do two things. First of all, well, instead of looking at the usual K0 of A, which is the Grothendieck group of the semigroup given by isomorphism classes of suitable one-sided modules, for example, left modules, you can do the following. You can consider, instead of projective and finitely generated left A modules, you can consider those that are actually bimodules. So isomorphism classes of A modules with the condition that on one side they should be projective and finitely generated. The point is that if you consider two such bimodules and you take the tensor product, the direct sum or tensor product over A, but this is the less trivial thing. If you take the tensor product, this is still finitely generated and projective on one side, but these are bimodules, so you can multiply them. And if you do the same construction as the usual thing that you do for K0, you form first with these bimodules, you form a semi-ring with isomorphism classes of these bimodules, and then you take the quadratic ring, you get something that you could denote K0 ring of A. So this is actually a ring, not just an abelian group, but and it has a relation with the usual K theory. The relation is that since these bimodules are projected and finitely generated on one side, you can forget that they are bimodules, and they define an element in the usual K theory K0A. So you have a map from K0 ring of A to K0 of A, where K0 ring is a ring, K0 of A is just an abelian group, and this map is a morphism of groups. It's not a, doesn't know anything about the ring structure of this object, but it is a morphism of group. And usually, in general, it's not injective, it's not surjective, so it's and inside, this is still too complicated to study in general, but inside we can consider the subring, which is generated by classes of line bundles. These line bundles in particular, since they are invertibles, these are invertible bimodules. Invertible bimodules are projective and finitely generated. So classes of these are inside here, and you can consider the subring they generated that I called the Picard ring because it reminds the construction of the Picard group of a manifold of an algebra. So this is what I call the Picard ring. For an AF algebra, K1 is 0, so I don't have to worry about K1. This is what I want to study. I want to study K0 and in particular these two objects, the Picard ring and this K0 ring. So the natural question is, when are line bundles enough to generate the usual K0, K0A? So the composition of these two arrows, I want to know when is it that it is surjective. The first is an embedding of rings. This is a morphism of abelian groups. So is it surjective in some cases? And the other question is, can we really put a ring structure here, some canonical ring structure, at least for some class of sister algebras, such that with this ring structure, this can be promoted to a morphism of rings, not just of groups. And this is what I did for this AF core of graph sister algebras. And I will just show the final result because it's very late. So let me show the final theorem, maybe. Okay, so the final theorem is this. Gamma is the adjacency matrix of E, which is finite and with no sinks. Gamma tilde is another matrix that I construct from gamma. I'm not going to tell you what it is, but it's something that you construct from gamma. If these two matrices are invertible over the integers, then you can prove the following. You can prove that there is an isomorphism of abelian groups from K0 of the AF core of your graph sister algebra to the abelian group underlying this ring. This is the ring Z of T, polynomials in T, modulo the ideal generated by the determinant of T gamma minus 1, where gamma is the adjacency matrix. So it's something very explicit.
Sorry, don't you have TT inverse? Is it the Laurent polynomial? I mean, K0 and the good cases.
So in this case, T will be. So here there is just polynomials, not Laurent. But in this ring, so this is a polynomial in T, not in T.
Yeah. So T T is
But
invertible.
actually, T will be invertible. Then you can prove that because of these two conditions, T is invertible.
So this is just the statement that K0 of the 0 degree part is the gauge equivariant K theory of the whole graph system algebra.
Well,
I mean, this is a well-known thing. I mean, for Leavitt path algebras, right?
Yeah.
You get K0. So for algebras, I think when you have no sinks, and maybe if you additionally have no sources, I don't recall exactly, but in that case, in a good situation, K0 of the 0 degree part is the same as K0 of graded projective finitely generated modules, which in the C-star setting will be the gauge equivariant K0.
Yes. Yes. Yeah. And this is just a statement about the abelian group K0. But then it says something more. It says that, okay, the explicit map is the one sending the class of the Lambda LK to the T to the power K. So this map is explicit. And the interesting part is that if you compose this map with the map from the Picard ring to K0, the composition is actually an homomorphism of rings. So in some sense, you have a ring structure on K0 because these two as abelian groups are isomorphic. So you can say, okay, I put here this ring structure. This ring structure in this sense is compatible with the tensor product of line bundles with this Picard ring or K0 ring if you want. Okay, but let me show in examples what you get. I wanted to show at least one example. Let me show just in the case of complex projective spaces, because this is where you get is one more proof if you want of these results by Arici, Landi, that were proved again by me, Piotr, and others. So this is one more proof. The one that you see here with n vertices and an arrow from one vertex to another, for every vertices are labeled from 1 to n. For every E and J from 1 to n, if E is less equal than J, then there is an arrow for each J. It means that from each vertex, you have arrows going to every other vertex to the right, including to itself. You have a loop at each vertex. So this is the graph of the graph C-star algebra is for some reason that I'm not going to explain is the C-star algebra of the quantum space CPN minus 1 cube. N-1 dimensional quantum complex projective space. This was proved in, there is a different definition of the C-star algebra of this quantum projective space. Then it was proved that is isomorphic to the graph C-star algebra of this graph in a famous paper by Young and Szymanski. And okay, this is a finite graph with no sinks. We can apply our theorem. The adjacency matrix is upper triangular with 1 on the main diagonal, which means that it is invertible. And the determinant of T gamma minus 1 is just T minus 1 to the power n, is the product of the elements on the diagonal. So in this case, our ring is this one. So if you call 1 minus T, you call it X. This is, we find again the ring of truncated polynomial as expected. And I remind you that T was the image of the line bundle L1. So this is really the 1x, 1 minus T is really the Euler class of L1, like in the classical case. Okay, so we find, you can write down from these in general, you have identities for every F-core of a graph C-star algebra. From the ring structure, you derive identities that are generalized, these identities for CPN minus 1. And in the case of quantum projective spaces, you can find, you get back what you expected, what was the original motivation to prove this general theorem. There are non-examples. Maybe I can just show one more example and then that's it, we can stop here. If you take this graph with two vertices and with the adjacency matrix 1, 1, 1, 0, this is our gamma. C star of V, this is the graph C star algebra is isomorphic to O2, to the Kunz algebra O2, even if it is isomorphic in a non-equivariant way. So the gauge action is different from the one on the bouquet graph, coming from the bouquet graph. If you use the bouquet graph, the one with one vertex and two loops, the F core is the car C star algebra. If you use this graph and the corresponding gauge action, the F core you can show by looking at the Bratelli diagram and that the realization of the F core as the groupoid C star algebra, you can show that this is in fact the C star algebra which parameterizes the Penrose tilings. It is the groupoid C star algebra of the groupoid whose objects are sequences of zeros and ones, but with one always followed by zero. And the relation is the relation of tail equivalence. This is the C star algebra that appears also in already in Kohn book and describes for some way parameterizes Penrose tilings. Okay, if you take this gamma and compute the ring, now the ring is isomorphic to z of 1 plus square root of 5 over 2, where this is the golden ratio. And you can write down explicitly this isomorphism is not very difficult. And the analog of the Theatod identities for CPN, in this case, are identities involving the Fibonacci numbers, which is not surprising for people working with Penrose tilings, and not surprising because this is the matrix whose powers generate the Fibonacci numbers. Again, there are analogies with projective spaces. Also in this case, both in this case and in the case of projective spaces, the case theory as a ring is generated by one line bundle by L1, which is also given by the class of a vertex projection. And I think this is a good point to stop. So thanks for the attention.
Okay, thank you very much for the nice talk. I have a comment. There is there was an early attempt by Christian Cassel to define an algebraic variant of Kasparov's K-theory, in which his K0 of AB consists of the bimodules, which are of finite type and projective as modules, as right modules on B. So yes, if you say A equal to B, then you get all the bimodules that are finitely generated and projective on one side.
Yes.
And this seems to be your K multiplicative, your K0 ring.
Yes, I mean, this is a very natural thing. The only thing is that I'm not really studying this, but the subring generated by invertible bimodules, because this is too complicated.
Yeah.
But if you send me the reference, it would be nice, because I didn't know about this reference actually.
Yeah, so what I mean is, in the end, because you started saying that one could consider the bivariant, the Kasparov K-theory of AA, right?
Yeah.
And then, well, you are kind of doing that, because you are, in considering K0 ring, this is some form of bivariant K-theory of AA. This is what that's what my point was.
No, I mean, what I want to say, okay, but if you send me this the reference, it would be nice, because actually I was looking for something.
Right now, I will do that. Let me.
But also I wanted to say, I mean, because this comment about the functoriality of KKAA is more related to the other paper that I didn't talk about today.
I recall. Yeah.
And what we do in that paper is a bit different. We basically, I can say in few words, the idea is simple, is that classically, instead of using vector bundles to define K0, you can use principal bundles. And principal bundles in the non-commutative case, they still make sense if you think of them as off-Galois extensions, so suitable modification of the notion of Galois extension. And basically, in this case, you get something, you get some kind of case theory generated by modules. So you use the idea is to pass from vector bundles to principal bundles, basically. So it's not really related. That one is not really related to KK theory. But in this class of examples, yes, for graph sister algebra, yeah.
The other comment is, at least in the case of Kunz algebras, so that there is only one vertex, I think the algebras are self-absorbing.
Yes.
Right? And the K-zeros, I mean, they are ultra, so UHF algebras, aren't they? And so if an algebra is self-absorbing, then a K0, from the fact that they are self-absorbing, I think K0 inherits a product structure.
Yes. So yeah, this is true. Yeah. But maybe I think that all O2 is self-absorbing or all Kunz algebras. I don't remember. O2 for sure, or not O2.
I mean, if I take mn infinity and I tensor it with itself, don't I get mn infinity? I mean, I'm inverting n. So if I invert n twice, I get inverted again.
Okay, so for UHF and infinity algebras, I mean, you can still do this trick of thinking of them as AF core of a graph sister algebra, and you get the ring structure that you would expect. You get, this was one of the examples that I didn't show. So, but it is true that you don't need this construction because you have, in principle, you have a map from A tensor A to A, which induces a ring structure in K-theory. The problem is that I tried to compute this explicitly.
Yeah, no. What I mean was, so at the end of my comment, there was a question. And the question is whether you get the same product structure. So here, you should take a look at the chat. In the chat, I put the paper by Cassel. And Devarshi Mukherjee commented that for self-absorbing sister algebras, K-top is multiplicative and gave a reference for that. So you might want to look.
Okay, I don't know how to see the chat while I'm sharing, so I will do later maybe.
Okay.
In screen sharing, I don't know if I can. Okay, yes.
Yeah,
okay,
you just push. Yeah. You just hit on chat.
Okay, and this says for self-absorbing sister algebra. Okay.
This is
no, I mean, it is clear that whenever you don't even need the self-absorbing, you just need, this is something also I try to do, you just need a map from A tensor A to A, which is a morphism of algebras, which is just the multiplication map if A is commutative, but in general you don't know what it is. Now, such a map for AF algebras, there should be such a map, but then I mean, computing explicitly the ring structure, I mean, I think it's just existence. I don't know if you can, I mean, since it exists, you know that there is a ring structure, but then actually computing it, I don't know if it is something doable.
Maybe for UHA, for n infinity, it should be doable, which would be the core of ON, right?
Yeah.
But anyway, are there any more questions or comments from the audience? If not, I will stop the recording now.